Suppose I give you some easy math problems and challenge you to arrive at the correct answer in minimum time. What would your strategy possibly be? You might think, okay, I will only have to be careful about my calculations and then I am through. What if I told you that this is not sufficient? Even if you check your calculations, there are still pretty high chances of committing mistakes. I call these mistakes blunders. The most common way to tackle these blunders is to be aware of them in the first place and keep your cool while solving the question. The purpose of this and upcoming video is to make you aware of some of these blunders. The topics which I have touched are basics of algebra, logarithms, equations and inequalities, coordinate geometry and calculus. You may or may not commit these blunders, but it is good to know about them beforehand. We cannot divide both sides of an equation by a variable which may be equal to 0. Consider this example. By seeing p minus 2 common on both sides, many might make a mistake that they cancel these two terms and they get x equal to 1 by 2p. But that is not the complete solution. Let me explain. The general strategy to solve these questions is to bring everything to one side and then factorize. If I bring p minus 2, this term to this side and then factorize, what I get is p minus 2 into 2px minus 1 equal to 0. Now see, the product of two terms is equal to 0. This happens when one of them is equal to 0. So case 1, when p minus 2 equal to 0, that is p equals to 2, whatever be the value of x, the equality will hold. So we can say that when p equals to 2, x belongs to the set of real numbers. Now let us assume when p is not equal to 2. So when p is not equal to 2, this term cannot be equal to 0. So this term has to be 0. So that implies 2px minus 1 equal to 0. But see, when p equal to 0, we get 0 minus 1 equal to 0. So this equation is inconsistent. If we put 0 here, this term is 0 and this is minus 2. So these two sides are becoming inconsistent. So when p equal to 0, there exists no solution for x. But when p is not equal to 0 and p is not equal to 2, then we can uniquely define x as 1 by 2p. So directly by seeing, we cannot tell that x equal to 1 by 2p. We have to first solve by cases. We have to first assume the values of p, that for which values what possibilities will arise. We have to compare it with the original expression, and then we can arrive at our final answer. When we square both sides of an equation, we can create some extraneous solutions. For example, if I tell you what is the square root of 9, then we always define it to be equal to 3. It is not minus 3. Although minus 3 square may be equal to 9, but when we say the square root of 9, we mean the positive square root of 9. So no sign is mentioned here means we denote the positive square root, and we always take it to be conventionally equal to 3. It is not minus 3, although minus 3 square can give us 9. So let us consider this example. To solve this question, we have to square both sides of this equation. We will square, but at the end we will verify whether the solutions that we get are really the solutions to this equation or not, because some of them may be extraneous solutions. So let me proceed. Squaring both sides of this equation, I get to 6x plus 40. Now when I simplify this, I will get bringing that to that side, 4x plus 14, or 2x plus 5 into plus 21 equal to 2x plus 7. Now I get another equation, so I will again square it. So after squaring, I will get So finally I am getting a quadratic equation, and I can find the solutions using the Sridharacharya formula or the quadratic formula. So using that I will get that the solutions are 4 or minus 14 by 3. So the general method to verify whether the solutions that we get are really the solution is to put this in the original equation and check whether the equation is satisfied or not. But you might realize that substituting these values might be too much time consuming. So I am telling a short trick. So the shortcut is that we must check whether the domain is satisfied or not. For example, this thing inside the square root must be positive, only then is the square root defined. In the set of real numbers, when we talk about square roots, we mean that whatever is inside must be positive, because if it is negative then it becomes a complex number. But since we are dealing with real numbers, that cannot be possible. So this thing must be positive, this thing must be positive, this thing must be positive. So when we put 4, you see that this thing is coming out, all of them will be positive because plus sign is here. And so, and when you substitute minus 14 by 3, again you will get that every of them is positive. For example, means minus 14 by 3 is approximately equal to minus 4.66. so when you will put this here, you will get that each of the numbers is positive. But I cannot conclude right then, because that minus 14 by 3 is the solution, because the most appropriate method is to put the values and check whether equality holds. I am just taking the domain, so you have to go one step further. See, I have squared here. In this step I have squared both sides to get this, and notice that I have squared here also. So I must check whether the equality is holded in this condition also, because I have squared both sides of this equation. Now see that when I put 4 here, this thing is positive, this thing is positive, it is satisfied. But when I put minus 14 by 3, this thing is positive, but this thing turns out to be negative. And I have told previously that square roots, when we put no sign before them, are always taken as positive. We do not write square root of 9 as minus 3, we write square root of 9 as the positive square root of 9. So in short, I can tell that if I want to tell square root of a is equal to b, we mean that both a and b are greater than or equal to 0. A has to be greater than or equal to 0 because we are talking in the set of real numbers, not complex numbers. And b has to be greater than or equal to 0 because we conventionally mean the positive or non-negative square root. Since no sign is mentioned here, it is positive. So see, when I put minus 14 by 3, this term is positive, but this is negative, and this one cannot be negative. So here is the catch. So minus 14 by 3 cannot be the answer. So x equal to 4 is the correct answer to this question. As mentioned previously, if I continue from that, the square root of x square can be written as mod of x. So this is a very important thing that we must note. Also, if a square equal to b square, that does not imply a equal to b. That implies mod of a equal to mod of b, or a equal to b comma minus b, means a may be equal to b or a may be equal to minus b depending upon the situation. So square root of x square is equal to mod of x. So using this knowledge, let us try to solve this question. The general strategy is to first multiply this term with this term, that is to generate sine theta or sine of alpha here, sine squared alpha, and then we can bring the term outside of the square root. So if I do just that, I will get that 1 minus cos alpha into 1 minus cos alpha. See, if I multiply 1 plus cos alpha with 1 minus cos alpha, I will get sine squared alpha plus 1 plus cos alpha 1 plus cos alpha. See, if I multiply 1 minus cos alpha with 1 plus cos alpha, I will get sine squared alpha. Now, many students make a mistake that seeing this square and this square, they bring it directly out of the square root. But we cannot do that directly. We have to put a mod sign. And we have to be very careful, especially in trigonometry, because trigonometry, the angles, the signs of the angles assume different values. Like the cosine, sine, they may be positive or negative in one quadrant. So that is why we must always put a mod. That is the safest way to solve any trigonometric question involving square roots. So if I put mod here, 1 plus cos alpha by sine alpha. Now so we are given another thing, that alpha belongs to pi to 3 pi by 2. So we have to simplify this further. Now we know that mod of a by b is mod a by mod b. So using that, I can tell that mod of 1 minus cos alpha by mod of sin alpha plus mod of 1 plus cos alpha by mod of sin alpha. Now if I draw the circle diagram using the all sine tan cos, see the angle is given in the third quadrant. This sine is negative, cos is also negative. So see, if cos is negative and I want this thing to be positive, what I can do is I can simply bring this out of the modulus, because see, if I bring this simply out of the modulus, this term is negative, so negative of the negative is positive, and I am eventually getting a positive term. And sign is negative in this case, and if I want to bring it out of the modulus, I have to put a negative sign onto it. And say this is negative, cos is negative, but it is still not more negative than minus 1. So if I simply put 1 plus cos alpha, my work will be done. And here in sin alpha, I have to put minus sin alpha. And if I substitute and simplify, then I will get my final answer as minus 2 by sin alpha. And that is the final answer. The logarithm of x to the base a is defined when x is strictly greater than 0 and the base a is strictly greater than 0 but not equal to 1. While solving logarithm questions, we must always verify our solutions with the condition for the logarithm to be defined. Consider this question. We have to solve for log of 6x square plus 23x plus 21 to the base of 2x plus 3 is equal to 4 minus log of 4x square plus 12x plus 9 to the base 3x plus 7. Now the general strategy is we have to factorize this, because when we factorize we get a nice expression for log, because log of a into b is equal to log of a plus log of b. So we can break the log. That is why we have to factorize this quadratics, and it is not too difficult to factorize this quadratic. If you see 6x square plus 23x plus 21 can be written as 2x plus 3 into 3x plus 7, simply by using middle term factorization technique. And 4x square plus 12x plus 9 can be written, see it is a perfect square, 2x plus 3 whole square. Now what we have to do, we have to simply put this and use the properties of log. And when we put that, say log of 2x plus 3 base, and this 2x plus 3, 3x plus 7, right? So now I'll make a substitution, that is log of 2x plus 3 to the base of 3x plus 7 equal to t. Now one more strategy, that whenever we make a substitution like this, we assume a function to be t, we always must note the domain and range of that function. So domain I have already mentioned previously, domain of the log function, and now I'm mentioning the range. The range is real numbers. So logarithm means two types of curves exist, like this and like this. So you can notice that the range is for real numbers, and whenever the range is real number, our means problem is little bit reduced, because I will show later that when the range is not real numbers, we have to assume separate cases for solving the question. But here such cases are not required, because the range is simply real numbers. So if I substitute the value, see using the properties of log, I can get this expression, and now I am finally getting a quadratic, 2t square minus 3t plus 1 equal to 0, and the solutions of this quadratic will be 1 and half. So now if I put this back in this expression, I am getting 2x plus 3 equal to 3x plus 7, that implies x equal to minus 4. And if I substitute this half, 2x plus 3 equal to root over 3x plus 7, which implies I am again getting a quadratic expression, 4x square plus 9x plus 2 equal to 0. And if I solve this, I will get x equal to minus 2 and minus 1 by 4. Now we have to put these values in the original question and check whether the domain is matched or not. See, if I put here minus 4, see this term is negative, the base is becoming negative. So minus 4 cannot be the solution. If I put minus 2 here, see minus 4 plus, so again the base is becoming negative. But if we put minus 1 by 4, we will see that the base is neither becoming negative, nor is the this term will not become negative, and it will not be equal to 1 also. Means the base will not be equal to 1 also. So minus 1 by 4 is the correct answer for this question. We cannot cross multiply in an inequality when we are not sure that the variable is either positive or negative. This is just because of the fact that when we multiply by some variable on both sides of the inequality, the sign of the inequality can change when the variable is negative, and it will not change when the variable is positive. So when the variable can assume both positive and negative values, we cannot cross multiply both sides of an inequality. So the best strategy is to bring everything to one side and then factorize. So for example, let me give another example. Like we have 2 by x less than 3. I cannot tell that x is greater than 2 by 3. No, that will be wrong. Because I cannot cross multiply by x. X is a variable, it may be also negative. So the best strategy is to bring 3 to this side and then simplify. So if I simplify this, that x minus 2 by 3, and I will reverse the sign of inequality, this expression I am getting. And then by our knowledge of wavy curve, we can solve this, that x is belonging to the interval minus infinity to 0 union 2 by 3 to infinity. So this is the correct way to bring everything to one side and then simplify. For this question also, if I bring 1 to this side and then simplify, what I am getting is this expression. Now I will multiply minus to both sides and change the sign of the inequality, and here. So now say we can factorize this expression. 1 is clearly a factor, and by the product of roots, if 1 is a factor, then 4 must also be a factor. So this here also 1 is a factor, and so 3 will also be a factor. See, now comes one more checkpoint. See here, x minus 1 is common factor, right? So we can cancel this common factor, but if it is 0, then this equation is not defined. So x cannot be equal to 1. We are cancelling it only with the assumption that x is not equal to 1, because if x is equal to 1, this will not be defined. Denominator is 0, so this is not defined. So we are assuming x is not equal to 1, and we are cancelling this. Then if we draw the wavy curve, see here, see, so this interval our solution lies, but we also have to exclude 1. See, 1 is coming in this interval, it is included in our solution space. We have to exclude that. So we will write our solution as x is belonging to the interval minus infinity to 3 union 4 to infinity, and we are excluding 1 because x cannot be equal to 1. This original expression is not defined in that case. One very important thing to note is that when a is greater than b, we can write a to the power m greater than b to the power m only when a and b are both greater than 0 and m belongs to the set of natural numbers. So squaring inequalities is possible only when both the terms are positive. If the both sides are negative, we cannot directly square both sides of the inequality. See here, root over of some expression is greater than this. So first thing that must always come to the mind is that whatever is inside the square root must be positive, because we are talking about real numbers. It cannot be negative, because then the whole thing will become complex number, and we don't want that. So we want that this expression is greater than or equal to 0. And if we simplify this, x minus 4 into x plus 2 less than or equal to 0. So this is where our x must lie, minus 2 to 4, done. Now one more thing that I have told previously is that, see, no sign is mentioned beside the square root, means we mean the positive square root. So whatever must will come of this output, whatever will be the output of this function, will be positive. So if this term is negative, so negative number will always be less than a positive number. It is very obvious, because if this term is negative, negative cannot be greater than a positive number. So we will solve by cases. We will first assume that this term is negative. 6 minus 3x is negative, or it may be equal to 0 in this case. So because we will check that now, that is x is greater than or equal to 2. So x is coming out as greater than or equal to 2. This term is 0, this term is non-zero, so it is positive. So positive number is greater than 0. It is satisfied. And second case, case 2, when this term is strictly positive, it is greater than 0, that implies x is less than 2. When that is the case, then these two are positive and we can square both sides. So squaring both sides, we will get greater than 36 plus 9x square minus 36x, right? So simplifying this, we will get 5x minus 14 into x minus 1 less than 0. So wavy curve, if we draw 14 by 5, it is approximately 2.8, not approximately, exactly 2.8. So x must be less than, so it will lie in this interval. Now say 2 lies somewhere here, and in our this case we assume that x is less than 2. So our final solution for this case will be x belongs to 1 to 2, and in another case we got that x is greater than or equal to 2. So we are getting that x belongs to 1 to infinity, but we also have to merge with this condition, that is take the intersection. See, here is 1, here is 4, and here is minus 2. X must lie in this interval. So when we take the intersection, we will get that x is belonging to the interval, open interval 1 to 4, and 4 is closed. So this is the correct answer for this question. Now let me solve this question. This is again an inequality. As told previously, we cannot directly cross multiply. It may be negative or it may be positive, depending on that the sign of the inequality will change. So we cannot cross multiply. We have to bring 1 to this 1 to this side and then factorize, sorry, not factorize, simplify. But if you notice that if I bring 1 to this side, I am getting a square root term and a linear term, and to simplify that will be too complicated. I have to again square, then I have to check, a lot of more, the solution will become more lengthy. So in this particular case, I will not bring 1 to this side, rather I will cross multiply. But I will make cases like, firstly though, I have to see that whatever is inside the square root must be positive. So 2x minus 1 is greater than or equal to 0, or is x is greater than or equal to half. This is the prerequisite. Now what I will do is, I will make cases, that is, firstly I will assume that x minus 2 is greater than 0. When x minus 2 is greater than 0, I can cross multiply. Notice that x minus 2 cannot be equal to 0. This is not defined. So two cases, x minus 2 greater than 0 and x minus 2 less than 0. When x minus 2 is greater than 0 or x is greater than 2, I can cross multiply without changing the sign of the inequality. In that case, I get 2x minus 1 is less than x minus 2. Now notice that this thing is positive. Whatever comes as the output of a square root is always positive by our definition. And so if some number has to be greater than a positive number, it has to be positive. Else a negative number cannot be greater than a positive number. Since this number is greater than a positive number, this number is eventually positive. Right, and see, since this both of them are positive, hence we can square both sides of this inequality. So squaring both sides and simplifying, we will get that x minus 1 to x minus 5 is greater than equal to 0. And so see, and we have already assumed that x is greater than 2, so 2 is somewhere here. Our solution space will be this one. X is belonging to the interval 5 to infinity. Now case 2 is when x minus 2 is less than 0. That implies x is less than 2, but x must be greater than or equal to half. So this is the case. Now see, when x minus 2 is less than 0, that is, if I notice very closely, When x minus 2 is greater than less than 0, then notice in this expression I can cross multiply, but I have to change the sign of the inequality. So cross multiplying, keeping in mind that the sign of the inequality will change, I will get this expression. Now see that this is positive and this is negative in this case. So positive number is always greater than a negative number. So all the x lying in this interval will satisfy this inequality. So our final answer will be x is belonging to half comma 2 union 5 comma infinity, half comma 2 union 5 comma infinity, and this is the correct answer for this question. While solving logarithmic inequalities, we have to be very much sure on whether the base is strictly greater than 1 or lies between 0 to 1. Because if the base is strictly greater than 1, we can put this base to this side without changing the sign of the inequality. But if the base is between 0 and 1, then the sign of the inequality will change. So firstly we must ensure that this number to which we have to find the logarithm, this number must be greater than 0. This is the prerequisite, and the base must also be greater than 0, but it cannot be equal to 1. So firstly we will check whether this term x square minus 10x plus 22 is greater than 0. So we can solve this by the quadratic formula and factorizing this 5 minus root 3 and x minus 5 plus root 3, this must be greater than 0. So 5 minus root 3 and 5 plus root 3, so x must lie in this interval. If I write the approximate value of this comes out to be 3.27 and this comes out to be 6.73. This is the approximate value. Now we know that for which values of x this is defined. We have to also find that for which values of x this is defined. So I will make two cases. That is case 1 when this expression is between 0 and 1. So this is one case. So when I will put this to this side, then the sign of the inequality will change. So now raising each power, see this power is greater than 1. 2 is obviously greater than 1. So sign of the inequality will not change. 2 to the power 1 2 and 2 to the power 0 1. So x is between 4 and 2 and 4. So when x is between 2 and 4, what I will do is x square minus 10x plus 22. So this sign will change. It's less than 1. So what I am getting 21. So x minus 3 into x minus 7 is less than 0. So I get that my interval will lie between this, but x must also lie between 2 and 4. So taking the intersection, x lies between 3 and 4. In this particular case, x belongs to 3 to 4. We have not taken the intersection with this, we will take it later on. So we are taking case 2, that is when this term is strictly greater than 0, strictly greater than 1. So that time we will get that x is greater than 4, and when x is greater than 4, this sign of inequality will not change, it will remain the same. So we will get x square minus 10x plus 21 is strictly greater than 0, or x minus 3 into x minus 7 is greater than 0. So x must lie here, but x must be greater than 4. So x belongs to 7 to infinity. So now we will draw our final solutions that we got 3, 4 and 7. X must lie here and here, but we have to take also the intersection with this case. So 3.27, which is 5 minus root 3, is somewhere around here. 5 minus root 3 and 5 plus root 3 is somewhere around here. So x must lie in this interval. So our final solution is x belongs to 3 to 5 minus root 3, and we will take the union with 7 to infinity. So this is the final solution. So we have to solve by these cases. That is, in one case the sign of the inequality will change and in one case it will not change. If p to the power q is equal to p to the power r, we cannot directly conclude that q is equal to r. it is one of the solution but not the complete solution. We have to first check for trivial cases like 0, 1 and -1, and only then after checking for these trivial cases can we conclude that Q is equal to R. Let me elaborate it. If P is equal to 0 and these whole terms are positive, Q and R are positive, 0 to the power 0 is not defined, so these terms has to be positive. So 0 to the power anything is 0 if the thing is not equal to 0. So 0 is equal to 0, equality holds. If this is 1, 1 to the power anything is 1. So whatever be the value of Q and R, equality will hold. And if this is -1, -1 to the power even is also 1. So for this case also equality will hold. And lastly, when Q is equal to R, equality will hold. So this is the complete solution set. Let me explain this with one question. The question is as follows, that is, so this is the question. We cannot directly say that this is equal to 7. No. We have to solve for the trivial cases first and then we can conclude. One thing that we must observe that for removing the modulus we have to do something, because directly we cannot compare also, because the modulus must be removed. One thing which we must notice that this thing is positive, so the LHS is positive, the left hand side is positive and the right hand side also must be positive, and if this right hand side is positive then x minus 1 whole to the power 7 must be greater than 0, which implies x minus 1 is greater than 0 or x is greater than 1. And when x is greater than 1, I can simply write mod of x minus 1 as x minus 1. So now my task becomes very simple. These two terms are becoming the same. X square 3 minus 2 log 9 base x equal to x minus 1 whole to the power 7. Now firstly we will assume that this term is 0. X minus 1 is 0. That implies x equal to 1. But see here x is the base. Base cannot be equal to 1. So it is not defined. So x equal to 1 is not the solution. Then we will see that this term is equal to 1. X minus 1 is equal to 1. That implies x equal to 2. See, none of the means according to the conditions of the logarithm for being defined, all the conditions are being held, none of the condition is violated, so x equal to 2 will be accepted as the solution. If we say that x minus 1 equal to -1 and then we get x equal to 0, we also have to check that these terms are odd or even. We have to check the parity, but before checking the parity we can notice that since it is the base and here also we can find the x term, it cannot be 0. The condition of logarithm will be violated. So x equal to 0 is not the solution. And we have worked out all the trivial cases. Finally we can compare the exponents. So now one simple thing that we can do, we will assume log of x base 3 as t. So when we assume that 2t, see these two will come out. So 2t minus 4 by t equal to 7. Now simplifying this, I will get 2t square minus 7t minus 4 equal to 0. So the solutions of this will be t equal to 4 and minus half. T equal to 4 and minus half. So if t equal to 4, x equal to 81 and t equal to minus half, x equal to 1 by root 3. So see, 1 by root 3 is less than 1. And what does mean? Well, we have firstly assumed that x must be greater than 1 because this is positive, this also must be positive. We have firstly assumed that x is greater than 1, but 1 by root 3 is less than 1. 1 by root 3 will not be accepted as the solution. So x equal to 81 and from here we got x equal to 2. So the final solution will be x equal to 81 and 2. This is the final answer. Now let me solve a very popular question from JEE Mains examination. So this question came in JEE Mains, a very popular one. We have to solve for this. This question can be related to the previous one, just that here we have this term to the power 0. So see, if this is equal to 0, 0 to the power anything, if it is not equal to 0 is 0. So it cannot be equal to 1. So this term cannot be equal to 0. So out of our trivial cases 0, 1 and -1, we have already eliminated 0. Now we will check whether 1 is one of the trivial solutions or not. So 1 to the power anything is 1. So 1 may be a solution. X square minus 5x plus 5 equal to 1. If we solve for this, then what we are getting is that x squared minus 5x plus 4 equal to 0, that implies x equal to 1 comma 4. So it satisfies, accepted. Then one more solution can be that this thing is minus 1. X square minus 5x plus 5 is minus 1, and in that case we will get that x equal to 2 comma 3, but this thing must also be even. So if we put 2, we will see that this thing is even, but if we put 3, this thing is not even, so 3 is already eliminated. One more case that will arise, that if this is equal to 0, anything to the power 0 is 1. If that is not equal to 0, 0 to the power 0 is not defined, else anything to the power 0 is 1. So x square plus 4x minus 60 equal to 0. From this we will get that x equal to minus 6 minus 10 comma 6. So we can factor x plus 10 minus 10 comma 6. So these are our complete solutions. Now in that question specifically, which came in the JEE Mains, they were asking for the sum. So the sum is 4 plus 1 5, 5 plus 2 7, 7 plus 6 13, minus 10 3. So 3 was the answer for that question. We must be very careful about the domain and range of a function. When we assume a function or an expression as a variable, we must be very careful about the values that that variable can achieve. Consider this question. A very common strategy to solve this question is to assume 2 to the power x as t. See, 4 to the power x is 2 to the power 2, and that is whole to the power x, so 2 to the power x whole square. So 2 to the power x equal to t can be used as a strategy to this question. So if I put 2 to the power x equal to t, I will get t square minus a into t minus a plus t. So this expression must be less than or equal to 0 for at least one real x. Notice that 2 to the power x is always greater than 0, strictly greater than 0. It can be considered to be equal to 0 at minus infinity, but we are not including that case, so it is strictly greater than 0. And this term, the coefficient of t squared is positive. So if we consider this expression, it is a parabola, or more specifically an upward opening parabola like this. And in the question we are asked to find the values of a for which this is less than or equal to 0 for at least one real x. So if I consider this as my x-axis, so the value of the y coordinate must be less than or equal to 0 for at least one real x. So this implies that it must have real roots, right? Less than or equal to 0, it can have one root, it is possible, but it can have two roots also, but it is not the only case. See, since 2 to the power x is strictly greater than 0, so the values which our t can attain is strictly greater than 0. So more specifically, this function must have real roots in the interval 0 to infinity. Means if for example, if this is 0 and if it has real roots like this, we will have no solution, because we are only concerned about the region that is greater than 0. We are not concerned about the region that is less than 0, because 2 to the power x is always greater than 0. It cannot achieve the value less than 0. So if this function means assumes negative value in the interval less than 0, that is not of our concern, because that will not be included in the graph of this function when we are concerned only for t is greater than 0. So this function must have roots, real roots, in the interval 0 to infinity. So when we have understood this, we can solve by two cases. So case 1, when both the roots are greater than 0, and case 2, when one root is greater than 0 and one root is less than 0. So when one root is greater than 0 and one root is less than 0, this is 0. Everyone must know that the step that we use is f of 0 is less than 0. So when we solve f of 0 is less than 0, we can say that one root is greater than 0, one root is less than 0. So solving this, we will get that minus a plus 3 less than 0, or a is greater than 3. This is from case 1. And case 2, when both the roots are greater than 0, what we can say is f of 0 is greater than 0, then this the x coordinate of the vertex of this parabola is minus of minus a, that is a by 2. This is the x coordinate, so x coordinate must be ahead of this 0 line, so a by 2 is greater than 0, and since it has real roots, discriminant must be greater than or equal to 0. So solving this, we get a is less than, I must put an equality sign here because we may have a situation like this also, so it is better to put an equality sign here. A is less than or equal to 3, then from here a is greater than 0, and if we simplify this, we will get that a square plus 4a minus 12 is greater than or equal to 0, a plus 6 into a minus 2 is greater than or equal to 0. So now we have to take basically the intersections, so 2 and minus 6, it is 3, it is greater than 0, so it must lie in this interval, and since it is less than or equal to 3 but greater than 0, so this is our required interval, so which is 2 to 3, and from this case we got that it is greater than 0, so final solution is x is belonging to the interval closed interval to open interval infinity, and this is the correct answer. One trivial assumption for an quadratic expression is that the coefficient of x square must not be equal to 0. That assumption comes into play in this question. See this quadratic expression very carefully. We are asked to find the values of a, parameter a, for which this is positive. So those who have learned location of roots might know that this term a square minus 1 must be greater than 0 and the discriminant must be less than 0. So it must be an upward opening parabola which is always above the x-axis. So in that case it will always be positive. But there is a catch in this question. See what happens if the coefficient of x square is positive. If the coefficient of x square is 0. If the coefficient of x square is 0, say for a equal to 1, the parabola will vanish and it will become a straight line, because when the coefficient of x square is 0, 1 degree is being reduced. It is turning from a quadratic expression to a linear expression, and we know that the graph of a linear expression is a straight line, so it will automatically turn into a straight line if we say that this term, the coefficient of x square is 0. Now one thing that is very common is that the straight line always cuts the x-axis if its slope is not in 0. If the slope of a straight line is not 0, that is, if I consider this as my coordinate axis, a straight line will always cut the x-axis, always. This is the x-axis, it will always cut it. Only in one special case, when it is constant, that is its slope is equal to 0. In this particular case it becomes parallel to the x-axis, that is, it is not cutting the x-axis, it is becoming parallel, it is a constant. So only in this particular case it will not cut the x-axis, that is, it will lie above the x-axis, but in all other cases it will always cut the x-axis. And if you carefully observe the expression for this curve, it is y equal to c, that is the coefficient of x, that is the linear term, is also 0. So one important conclusion is that in a quadratic expression, when the coefficient of x square and the coefficient of x both are equal to 0, then we get a constant polynomial which can always be positive if this term constant is positive. Say 2 is positive, if I put a equal to 1, this is becoming 0, this is also becoming 0, and 2 is already greater than 0, so our condition is satisfied. So this is one particular case which we will not get by solving in the traditional method. We have to analyze the graph and we have to know that this also happens, that is, when the x square term vanishes, the linear term also vanishes, we get a constant term, and that constant term, if it is positive, this whole expression will also be positive in that particular case. Now let me proceed with the solution. Generally we have to solve like this, that is, a square minus 1 is greater than 0 and discriminant is less than 0. I am not showing the solution, means if we solve like this, we will get that a minus 1 into a plus 3 is greater than 0. in this particular case, in this discriminant case, and in this case we will get a plus 1 into a minus 1 is greater than 0. So it is 1, it is minus 3, and it is minus 1. So our solution space will be here. X is belonging to the interval minus infinity to minus 3 union 1 to infinity. But as I have explained right now, that 1 will be included in the solution, because if I put 1 here, x square term and x term both vanishes and I get 2, which is positive. So condition is satisfied and 1 will be in the closed interval, and else the solution is correct. So this is the appropriate solution for this question. This question is basically my video in a nutshell. If you have understand the crux of my video, you should be able to solve this question, though I admit it is a really tough challenge. This question came in the JEE advanced examination. You may pause this video to give this question a try and then keep watching for the solution. Means the thing that makes this question really tough and challenging is that when you get the solution, you have to match the solution with the condition given in the question. For that reason, I have also put the exact problem statement here. The problem statement matters. Whatever you get as the solution must be matched with the problem statement. That is it is like the general strategy for any tough questions. Means whatever you get as a solution, we get the solution only after manipulating the original expressions. So the solutions that we get must be checked with the original expression or the original condition given in the question. We must not check the solution with the expression which we have manipulated. Means after simplifying the what expression we get, we must not check the solution with that expression, because that expression is not always correct. We must always check the solution with the expression that is given in the question. Now let me proceed with the solution. Everyone knows that the formula for the sum of infinite terms of an GP is equal to a by 1 minus r. So writing that, I can tell that s of k equal to a, which is k minus 1 by k factorial, a 1 minus 1 by k, and simplifying this, k minus 1 by k factorial by k minus 1 by k. So I will get that 1 by k minus 1 factorial. Right. Now by seeing this term and the factorial term, a common hint is that a telescoping sum will be formed, because else there is very little chances of calculating the sum of a factorial. The sum of a factorial is most commonly calculated using telescoping sum. So we have to convert this into a telescoping sum. See here, there is x minus 1. One hint is that we must convert it into x minus 1 whole square. Then I can cancel out one x minus 1 and then hope to get one telescoping sum. So simplifying that, x square minus 3k plus 1 by k minus 1 factorial. See, I can write it as x square minus 2k plus 1 minus k by k minus 1 factorial. Now simplifying this, I will get k minus 1 by k minus 2 factorial minus k by k minus 1 factorial. See, this is vn minus 1. See, if I put k plus 1 here, this comes and this comes. So this is exactly what we wanted, and we are getting the telescoping sum. Now we can calculate our answer, but no, we cannot calculate our answer right now. We have done one mistake which we have to find out. See, we have to first put the values and then check. For example, here check that we are asked to find for k equal to 1 to 100. When k equal to 1, the common ratio r is 1. So we know that when mod r is less than 1, the sum of infinite terms of a GP is defined. But here we are getting that common ratio is 1, but still the sum is defined. Why? Because if you put k equal to 1 here, you get that a is equal to 1. So it is a constant GP whose first term is 0. So all the terms are 0. Now whatever be the value of r, see here a is 0, so all the terms are 0. So the sum when k equal to 1, s1 is 0, but put k equal to 1 here. you get that 1 by 0 factorial, and 1 by 0 factorial is defined as 1. So s of 1 is coming out as 1 according to this manipulation, but we cannot calculate using this expression, and this is the catch, or this is the learning, that we must always check our answers with the expressions mentioned in the question. See, in the question we are given this expression, and using this expression we have derived this. So the sum for k equal to 1 must be calculated from the expression given in the question and not from the one that we have derived, because we have done one mistake here. If k equal to 1, we cannot cancel out zeros like this, like zeros cannot be cancelled, so this step is completely invalid. So that is one catch. And second catch is that here modulus is given, so simply if I put summation over this, that will be wrong. I have to first check where this is positive and where this is negative. So for k equal to 1 I have already found it. For k equal to 2, see what the term is coming, a equal to 2 minus 1, 1 by 2, so 1 by 2, and r is 1 by 2, so 1 by 4, something like that. So this is a normal sequence, means the sum of this can be calculated using our formula. So we are calculating the sum, it is coming out as 1 by 2 minus 1, 1 factorial, which is 1. And say this term, if I put k equal to 2 here, 4 minus 3 to the 6 plus 1, 5 minus 1, so this term is coming out as minus 1, but we want the modulus, so we'll take minus of minus 1, which is plus 1. For k equal to 3, this is positive, but say 9, 3 is a 9 minus 9 plus 1, so this is now coming out as positive, and as the value of k increases, this term will become positive, so no need to check further. So what we have done is basically we have calculated the value of s1 as 0 and s2 we have calculated as 1, and s3 everything we can calculate using means not s3 but these times s3 we can calculate using this expression. So if I want to calculate this sum, that is k equal to 1 200 k square minus 3k plus 1 times sk. For k equal to 1 I get 0, for k equal to 2 I get, this is minus 1, mod will be 1, this is 1, and for k equal to 3 I can directly use this formula. So it goes from 3 to 100, so here 3 term will come, 3 minus 1 2 by 1 factorial minus 100 by 99 factorial, so 3 minus 100 by 99 factorial, and we have to add 100 square by 100 factorial to this. Notice that these terms cancel and our answer is 3, and 3 is the correct answer for this question.